Hey guys, here is a massive summary of what you need to know for your first chemistry paper. In here we're going to be going over everything, but we're only going to be doing it quickly. If you want to make sure that you know absolutely everything, you want to get knowledge checklists, thousands of questions, links to videos, equations that you need to learn, film you need to recall, then you can get that all for free on my website in my revision guide, or if you want to one-click order it, you can get that over on Amazon. Here we have our wonderful, beautiful periodic table. It is a list of all the elements which are known to exist. Elements are a single type of atom. An atom's a very, very small thing. The word atom is actually Greek for uncuttable. And when they named them, they thought it was the smallest thing possible. The periodic table tells us loads and loads and loads of information about the elements, the range of elements that are known to exist. There are still loads yet to be discovered. A compound is two or more elements that are chemically bonded together. That's the important thing. Chemically bonded together. Here we have the structure of an atom. We have electrons that are on the shells around the outside, protons that are in the middle, and neutrons that are in the middle. And this bit in the middle here is collectively called the nucleus. Protons are in the nucleus. They have a mass of 1 and a charge of +1. Neutrons are also in the nucleus. They have a mass of 1 and a charge of 0. Electrons are in the outer shells. Their mass is 1/2000 and they have a charge of -1. On the periodic table you will see lots of boxes like this. This tells you all about the elements. This is the element's name, the symbol, and there are two numbers. This is the atomic number, and this one is the mass number. Now for these, location doesn't matter. Different textbooks, different sheets are going to put them in different locations. The larger one is the mass number, and the smaller one is the atomic number. The atomic number tells us the number of protons and the number of electrons in an atom. The mass number is the number of protons plus the number of neutrons. So here we have calcium. The smaller number is the atomic number, the large number is the mass number. And if you want to find the number of protons, it is simply the atomic number, so in this case 20. The number of electrons is also the atomic number, so again 20. The neutrons is the mass number, which is 40, minus the atomic number, which is 20, equaling 20. You need to be able to take a set of words and turn it into a balanced symbol equation. So there is quite a lot for you to do here because you need to remember the chemical symbols for quite a large number of things. Water is H2O. That turns into hydrogen gas, which is going to be H2, plus oxygen gas, which is going to be O2. And now we need to balance it. Draw a line down the middle, circle everything, and list what we have. We have hydrogen, we have oxygen, we have hydrogen, we have oxygen. Count the number of things. 2 hydrogens, 1 oxygen, 2 hydrogens, 2 oxygens, sorry. So we need to increase the number of oxygens on this side because you see there aren't enough. Then we have to add another H2O, put that in a circle, redo our numbers. We now have 4 hydrogens and 2 oxygens. So our oxygens are balanced, but now our hydrogens, we have more on this side than we do on this side, so we need to add more hydrogens here. Again, the only thing we can do is to add a whole another bubble. We now have 2 hydrogens here, 2 hydrogens here, making 4 in total and 2 oxygens. So now we have 4 hydrogens on this side, 2 oxygens, 4 hydrogens and 2 oxygens. We need to rewrite that neatly for the examiner, so we have 1, 2 bubbles of H2O turning into 1, 2 bubbles of H2 plus 1 of O2. I seriously recommend you learn at least these formula. Carbon dioxide is CO2, water, H2O, oxygen gas, O2, hydrogen gas, H2, nitrogen gas, N2, ammonia, NH3, hydrochloric acid, HCl, sulfuric acid is H2SO4. Elements, pure things. Compounds, 2 or more different things chemically bonded together. Mixture, lots of different things, some of them chemically bonded, some of them not. When you have mixtures and you want to separate them, there are a number of different things you can do. Distillation, where you're going to separate things off by boiling point, so things that have a different boiling point will distill at different temperatures. Evaporation, where we are going to remove the liquid and leave solids that have been dissolved in the liquid in the dish. Filtration, where we have large particles of solid in the liquid. The particles of solid will stay in the filter paper and the liquid will drip through. And fractional distillation, where you can take things off at different boiling points. We haven't always known that an atom had a nucleus and electrons orbiting around the outside. We used to have a plum pudding model, where we had a large cloud of positive charge with negative electrons dotted throughout, a bit like a Christmas pudding, which is why it's called the plum pudding model. Rutherford and Marsden did an experiment to test the plum pudding model. They took an alpha particle gun, and alpha particles are positively charged, and they had a sheet of very thin gold foil. And what they did is they fired alpha particles at this sheet, and the majority of them went straight through, which was a bit weird. Some of them got deflected a little bit, and some of them got deflected a massive amount. And this suggested that there was a centre which was positive, a small part that was positive, and then a large section all around which was negative. And this led to the development by Bohr of the nuclear model that we use today. The model of the atom has changed quite a lot over time. You don't need to know all the details of this, you need to know that Rutherford was responsible for discovering the nucleus and protons. That Chadwick discovered neutrons. And that Bohr is our current, or developed our current model. The periodic table gives us loads and loads of information. The first bit of information it gives us are about groups. Now groups go down the periodic table. Group 1, group 2, 3, 4, 5, 6, 7, 8, or group 0. Groups tell us the number of electrons on the outer shell. So things in group 1 are going to have 1 electron in the outer shell. Things in group 2 are going to have 2 electrons in the outer shell. Group 6, 6 electrons in the outer shell. Group 7, 7 electrons in the outer shell. Periods go across the periodic table. So here is our first period, the one that everyone always forgets because it's only got hydrogen and helium in. Here is our second period. Here is our third period, and the periods relate to the number of shells that things have. They also remind us how many electrons are in each shell. So in the first period there are 2 elements, which means there are going to be 2 electrons in that shell. In the second period there are 1, 2, 3, 4, 5, 6, 7, 8 elements, which means there are going to be 8 electrons in that shell. And we can use this information to tell us about the electronic configuration. Here we have magnesium. Here is magnesium on the periodic table, and we can see that the number of electrons it has is 12. It is in group 2 and it is in period 3. So that tells us it has 12 electrons in total. It has 2 electrons on the outer shell, because it's in group number 2, and it has 3 shells because it is in period number 3. So when we want to draw the electronic configuration of magnesium, we know it's in period 3, it's going to have 3 shells. First thing we can do is draw 3 shells. 2, 1, 2 go on the first shell. 1, 2, 3, 4, 5, 6, 7, 8 go on the second shell. That's the most that can fit in that shell. That brings us up to 10, 10, 11, 12, 2 electrons on the outer shell. From the periods, we know that the first shell can hold a maximum of 2 electrons, the second shell can hold a maximum of 8 electrons, the third shell can hold a maximum of 8 electrons, and then you only need to know up to calcium, so another 2 for your GCSE. Here we have sodium, and it has an atomic number of 11, which means it's going to have 11 protons in the nucleus, and protons have a positive charge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now in the atom it has 11 electrons drawn on here. Electrons have a negative charge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now in an atom, the positive charges and the negative charges cancel each other out, so the overall charge on the atom is going to be 0. However, when sodium makes an ion, this electron here goes away. So it still has the same number of protons, it's still sodium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But it's lost an electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has one more proton than it has an electron, meaning this is going to have an overall positive charge. Metals are going to lose electrons, and when we lose electrons we get positive charges, and non-metals are going to be gaining electrons, and when we gain electrons we get negative charges. Things in group 1 are going to lose 1 electron, so are going to be +1 ions. Things in group 2 are going to lose 2 electrons, so are going to be +2 ions. Things in group 6 here are going to gain 2 electrons, so are going to be -2 ions, and things in group 7 are going to gain 1 electron, so are going to be -1 ions. This beautifully coloured periodic table is because of lots of different groups, lots of different categories on the periodic table. Group number 1 are also known as alkali metals. Group number 2 are the alkali earth metals or alkaline metals. Group 7 are the halogens. And group 8 are the noble gases. The big chunk in the middle are the transition metals. Our periodic table hasn't always looked like this. The first attempt at a periodic table was by Newlands in the 1800s. He tried to group things into octaves and rate them by pattern, which is a really good idea, except we have oxygen and iron in the same group, and they had very different properties. He arranged them by mass, but he didn't leave any gaps, and he tried to force things in to have similar patterns or properties as other things, and it didn't really work. Mendeleev was the next person to have a go. He also arranged things by mass, but the key thing is that he left gaps in his periodic table, and because he arranged things so that they were in groups with similar patterns, and he left gaps, he could predict the properties of elements that have yet to be discovered, and he was correct in his predictions. A few years after he developed his periodic table, a couple of new elements were discovered, and they fitted in really, really neatly, really nicely to his periodic table. So this week's table was accepted. It has changed ever so slightly by then. We now arrange things by electronic arrangement, but that's a very, very subtle difference. The group right on the far right hand side are group 8 or group 0. These are the noble gases. They have a full outer shell. And because they have a full-outer shell, they don't want to gain or lose any electrons, which means they are really, really unreactive. And because they are unreactive, they actually have quite a lot of uses. Helium we use in balloons, and they are also used in neon lights, as you can see here in the amazing city of Osaka. Moving over one group to group 7, we have the halogens. We are still in the non-metals, and these are going to go around as diatomic molecules, which means their formula is going to be for chlorine gas, Cl2, fluorine gas, F2, bromine gas, Br2. They're going to go around together in pairs. Because they only want to gain one electron, a nice easy way for them to do that is sharing an electron with something else that is the same. So fluorine here can easily gain an extra electron by sharing it with another fluorine. They are highly reactive because they only want to gain one electron. And the most reactive ones are going to be at the top. Boiling point is going to change as we move down the group. So things are going to have a low boiling point or a low melting point are going to be at the top. High boiling point or high melting point are going to be at the bottom. When they react, they're going to gain an electron. Meaning they're going to form -1 ions. And gaining an electron is a reduction. They're going to react violently and rapidly with group 1 metals because group 1 metals want to lose 1 electrons. For example, sodium, which is a soft grey metal, will react very violently, very readily with chlorine, which is a yellow gas, to form sodium chloride, which is a white powder or salt. A more reactive element will displace a less reactive element. So here we have sodium iodide reactive with bromine. Iodine is here below bromine on the periodic table, so bromine is more reactive, so it will displace iodine in the compound, forming sodium bromide and iodine. Whereas if you try and react bromine gas with sodium chloride, chlorine is higher than bromine on the periodic table, so it's more reactive. You are going to get no reaction because bromine cannot displace chlorine out of this. These are commonly known as displacement reactions. The halogens are mostly used for sterilising things. For example, chlorine, you're commonly going to know that as from swimming pools. Halogens want to gain 1 electron, so the most reactive ones are at the top. That's where there's least shielding between the electron they want to gain and the nucleus. Your alkali metals react very violently with water, and this is where you're going to see some flames coming from, some different colours coming from. This is one of the things that we use to make the different colours in fireworks. So the lovely, lovely lilac flame from potassium we can use in fireworks. If you've seen these in school, these are soft grey metals which are easily cuttable. They need to be kept in oil so it doesn't react with oxygen or with the water in the air because it's a very, very violent reaction. When the metal reacts with oxygen, we're going to get a metal oxide, which if you've seen these in school, when it was cut, it was shiny, but it soon started to dull. The dullness is the metal oxide. The metal plus water is going to form a metal hydroxide. This gives it its name, it's alkaline metal, because the metal hydroxide is going to be alkaline. You can see that by the change in indicator if that's what your teacher did. And you will also notice this is a very exothermic reaction. It released a lot of heat. It also released hydrogen gas. That's what the fizzing was. The reactivity is most reactive at the bottom and least reactive at the top. Things at the bottom are going to have a low melting point or boiling point, and a higher melting point or boiling point at the top. Alkali metals want to lose an electron, and the ones at the bottom are most reactive because there is more shielding between the electron that they want to use and the positive nucleus in the middle. Solids have a very, very fixed structure. Their atoms may wiggle a little bit, but it is around a fixed point. There is going to be some movement and some vibration, but they are not flowing at all, and they can't be compressed. Liquids have much more movement around, but they are not in a fixed position. They can flow, but they can't be compressed. Gases are very, very free to move. There's lots of movement going on in here. It is not around a fixed position. They do a lot of moving. They can flow and they can be compressed. Going from a solid to a liquid is melting. From a liquid to a gas is evaporating. Going in this direction, we are putting energy in. Going in the other direction, energy is coming out. So from gas to a liquid, it is condensing. From a liquid to a solid, we are freezing. A compound has a melting point of 19 degrees, melting point, and a boiling point of 74. Boiling point, what is the state at room temperature? Room temperature is about 25, 27. So, when it boils, it turns from a liquid into a gas. So above there, it is going to be a gas. And below there, it is going to be a liquid. Melting point, we are turning from a solid. So this way is going to be a solid, and above there is going to be a liquid. So at room temperature is going to be a liquid. Now the other important thing to remember about boiling point and melting point is that the opposite is the same number. So boiling point is equal to condensing point. And melting point is equal to freezing point. We just talk about boiling point and melting point instead of condensing point and freezing point. They are exactly the same number. So if the boiling point is 74, the condensing point is 74. If the melting point is 19, the freezing point is 19. State symbols tell us what state something is in. So an S is a solid, L is liquid, AQ is aqueous, and G is gas. If you see state symbols in an equation, the answer generally refers to them. If you see something that's liquid and liquid, or aqueous and aqueous going to a solid, it is going to turn cloudy. If you have a liquid and a solid, or a liquid and liquid, and a gas is produced, you're going to see bubbles, or a loss of mass, bubbles or fizzing. Ionic bonding is the transfer of electrons from a metal, which is on this side of the periodic table, to a non-metal on this side of the periodic table. Anything that is in group 1 is going to form a +1 ion, group 2 a +2 ion, group 6 a -2 ion, group 7 a -1 ion. Here we're going to make magnesium oxide. Magnesium is in group 2, so it has 2 electrons in its outer shell. Oxygen is in group 6, so it has 6 electrons on its outer shell. In ionic bonding, oxygen is going to keep the electrons that it's already had, and the electrons that were with magnesium are going to be transferred to oxygen. We call these dot and cross diagrams because one element has a dot for electrons and the other element has a cross for electrons. We then draw square brackets around these and indicate the charge. So magnesium has lost 2 electrons, so it's going to have a +2 charge. Oxygen has gained 2 electrons, so it's going to have a -2 charge. Covalent bonding is the sharing of electrons between 2 non-metals, these up here. And these are the common ones you need to know how to draw. For each of these, you need to be able to give the name, the formula, be able to draw it with lines, and be able to draw the dot and cross diagram. So hydrochloric acid or hydrogen chloride, 1 element of hydrogen, 1 element of chlorine. Ammonia, NH3, nitrogen in the middle, 3 hydrogens coming off around the side. Methane, CH4, carbon in the middle, 4 hydrogens branching off it. Hydrogen, H2, very simple one there. Chlorine, halogens go around as diatomic molecules. Oxygen, we're getting a bit tricky now, has a double bond. Each line is equal to a pair of electrons. Here we have 2 lines, that is 2 pairs of electrons. We need 4 electrons being shared in the middle. And nitrogen has a triple bond, 2, 4, 6 electrons being shared in the middle. If in the exam they give you a picture and ask you to link the formula of it, you simply need to list what we have. So in the first one we have carbon and we have hydrogen, and then we need to count them. 1, 2, 3, 4, 5. Carbon, 5. Hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Last one, carbon, hydrogen, oxygen. We have 1, 2, 3 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 1 oxygen, so we don't need to put a number after that. It's really important that you write things in the right size and in the right place, so that is incorrect because your numbers are too big. That is incorrect because your numbers are in the wrong place. Metals are made up of positive atoms in a sea of delocalized electrons, and these electrons being free to move is the reason that metal can conduct electricity and why it's so good at conducting heat. An alloy looks slightly different to a metal. We still have our positive ions, we still have our delocalized electrons, but there's something else in there as well. This may be another metal it's alloyed with, or it may be something else like carbon that it's alloyed with. Pure metals have layers. Layers can slide across each other. Because they have layers and because they can slide across each other, they are soft. Alloys don't have layers, or they have distorted layers. And the distorted layers cannot slide. And because the distorted layers cannot slide, it means they are hard. Bit of a mental break here for you guys, just a tiny pause. You are doing so well. Let's keep going, we are nearly there. Here we have sodium chloride. Sodium are the grey bits you can see, and chlorine are the green bits you can see. The blue lines are the electrostatic interactions, the electrostatic attractions. Because the way we get you to draw ionic bonding is really false. It's not just one sodium combining with one chlorine. It is this massive lattice of sodiums and chlorines, or whatever we're looking at, bonding with everything else. So one sodium here isn't just going to be bonding with the chlorine next to it, or the chlorine that it's exchanged electrons to. It's going to be bonded with all of the other ones above it, next to it, behind it, in front of it, everything that it can reach. So this ionic bonding is a massive network, not just the small things that we get you to draw in class. So for ionic compounds, the structure is a giant ionic lattice. Properties, it is going to have a high melting point, high boiling point, and it is only going to conduct when molten or dissolved. This is because the ions need to be free to move. For simple covalent compounds, such as water, carbon dioxide, oxygen, nitrogen, hydrogen gas, hydrochloric acid, or methane, oxygen gas, or water, as we have here, they are very small structures. They have covalent bonding. Their properties is that they have low melting points, and boiling points. They're generally going to be a gas at room temperature or a liquid at room temperature. They do not conduct electricity. For giant covalent compounds, ones made of carbon, such as graphite, diamond, or any fullerenes or silicon dioxide, they are going to have a giant covalent structure. Their properties are high melting and boiling points, and they do not conduct, and they do not dissolve. Here we have diamond. It is a giant covalent compound, or giant covalent lattice. It is made of carbon, pure carbon, nothing else in there, and each carbon makes 4 bonds. So in the video you can see that the carbon is the black bits, the covalent bonds are the red bits, and each carbon is bonded to 4 other carbons. Obviously the ones on the edge aren't bonded to anything, but if you try and look in the middle you can see that they are bonded to 4 other things. The properties of diamond that make it really useful is that it's incredibly hard. It's very rare, it's hard to find, it's also very beautiful, which makes it very precious. But the main thing is that it's incredibly hard, so we can use it in drills. Graphite is also a giant covalent compound. It is like diamond, pure carbon, but each carbon makes 3 bonds to other carbons, not 4 like in diamond. The properties are that it is soft and it conducts electricity. Because it is in sheets and there is a spare electron floating around in between these, that means it will conduct electricity. Graphite is what you find in pencils, graphene is just a single sheet. If we were to compare diamond and graphite, they are both made of pure carbon. Graphite is made of 3 carbon-carbon bonds, diamond is made of 4 carbon-carbon bonds. Graphite is soft, diamond is hard. Fullerenes are either carbon nanotubules or Buckminsterfullerenes, which are balls. These are again all made of pure carbon. They make 3 carbon-carbon bonds, but unlike graphite, which is soft, these are incredibly hard. Buckminsterfullerene can be used as a lubricant in things that need lubricating, like electrical cycles or some parts of machines. It can be used for reinforcement, so where you need a very, very strong, very, very light things like aircrafts or bicycles. They can also both be used, or in the future be used, for drug delivery. And fullerenes, carbon nanotubules, Buckminsterfullerenes, there are loads and loads of potentials for these, but they haven't been realised yet. With polymers, whether they have cross-links or not, are going to determine what their properties are going to be like. So polymers that do have cross-links are very, very fixed in place. These are going to burn upon heating, whereas polymers without cross-links are going to melt upon heating, because these polymers can slide across each other, whereas these ones cannot slide across each other. You can measure the mass or volume of reactant or product by collecting the product, say in a gas syringe, or using a scale or balance to look at how the mass changes as a reaction progresses. Whenever you are measuring something, there is going to be a degree of uncertainty, whether it's a burette, a measuring cylinder, or a beaker. You need to look for the bottom of the meniscus always, because there is going to be this difference, this dip between where it looks at the top and where it is at the bottom. And you can say whether it is on the line or in between the line, but you can never say it that accurately, because it might be a quarter of the way or 3/4 of the way to the next line. So while you try and measure things as accurately as you can, there is always going to be a degree of uncertainty. When we are working out concentration, that is going to be your amount divided by your volume. Concentration is measured in moles per decimeter cubed. Amount is in moles and your volume is in decimeter cubed. The new style exams means there are a lot of wordy questions that incorporate a lot of skills all at once. In this question, you need to first of all recall the formula for things, then balance the equation. So hydrochloric acid is HCl, magnesium is Mg. Now we need to work out the products and the formula of the salts. A metal plus an acid is going to give us salts plus hydrogen. Hydrogen's the easy bit. It is H and then 2 because it goes around as a diatomic molecule. The salt is going to be magnesium chloride, but we need to know that magnesium is a 2+ ion and chlorine is a 1- ion. So it needs to be MgCl2 so that there are 2 negative ions for each positive ion. Now this is supporting a lot of skills, recall of the formulas, working out the salts, the products, so working out what type of equation it is, and then after all of that we need to balance it. So to balance our equation, we draw a line down the middle, list what we have: hydrogen, chlorine, magnesium. Hydrogen, chlorine, magnesium is really going to help you if you keep things in the same order. Circle the compounds that we have. List the numbers of things. So we have 1 hydrogen, 1 chlorine, 1 magnesium, 2 hydrogens, 2 chlorines, 1 magnesium. So you can see straight away we need some more hydrogens and some more chlorines. The easiest way for us to do that is to add another HCl on there. Then redoing our numbers, we have 2 hydrogens and 2 chlorines. That is balanced. Writing it out neatly for the examiners, because just leaving it like this won't get you the marks. We have 2 bubbles of hydrochloric acid plus magnesium turns into magnesium chloride plus hydrogen. When you are working out the MR, which is the relative formula mass, you need to take all of the ARs, which is the relative atomic masses, and add them together. Now the mass, remember, is the larger number of the two. Doesn't matter where it's located, it is the larger number of the two. So hydrogen has a mass of 1 and we have 2 of them. Sulfur has a mass of 32. Oxygen has a mass of 16 and we have 4 oxygens. So 1 times 2 is 2 plus 32 plus 16 times 4, which is 64. Add those together, we get 98. Excellent work so far, guys. Well done. Only a little bit longer. Let's keep going. Tiny mental break and then we can keep going. A mole is not a rather cute blind black furry thing, but it is the unit for the amount of a substance, and that is going to be 6 times 10 to the 23 atoms, ions, or molecules. And that is because that is the number of carbon atoms in 12 grams of carbon. So our equation for this is going to be moles is equal to mass over Mr. This is an incredibly complicated question which combines a lot of skills. First of all, you have to work out the formula of things, work out the equation, balance the equation, and then finally work out the amount of hydrogen peroxide. We have hydrogen peroxide decomposing into water, H2O, and oxygen gas. Now we need to balance the equation. Hydrogen, oxygen, hydrogen, oxygen, 2 hydrogens, 2 oxygens, 2 hydrogens, 3 oxygens. So we can increase that by putting more oxygens over this side, H2O2, giving us 4 hydrogens, 4 oxygens. Now we need some more hydrogens and oxygens over the right hand side. Pop another H2O on there. And we have 4 oxygens and 4 hydrogens, giving us a final balanced equation of 2 hydrogen peroxides making 2 water and 1 oxygen. Now we need to know how much oxygen gas is given off from 40.8 grams of hydrogen peroxide. The first thing we do is to work out the masses involved in the equation. Hydrogen has a mass of 1 and there are 2 of them. Oxygen has a mass of 16 and there are 2 of them. That is 2 plus 32, giving us 34. And because there are 2 of them, that gives us a total of 68. Hydrogen is 2. 1 times 2 equals 2. Oxygen is 16. 2 plus 16 gives us 18. 18 times 2 gives us 36. And then oxygen is 16 times 2, giving us 32. So we can say that if we had 68 grams of hydrogen peroxide, it would decompose into 32 grams of oxygen. But we don't have 68 grams of hydrogen peroxide. We have 40.8 grams of hydrogen peroxide, and we need to find how much oxygen that decomposes to. This is now just a ratios question from maths. I'm going to put a 1 in there. To go from 68 to 1, we need to divide by 68. So that's what I need to do on the other side as well, divide by 68, giving us 0.47. To go from 1 to 40.8, we need to times it by 40.8, which is exactly what we need to do over this side, times 40.8, but I don't want you to clear your calculator. I want you to keep the number in your calculator. So 0.47, or the long number in a calculator, times 40.8 gives us 19.2 grams. If you had cleared your calculator and got just did 0.47 times 40.8, you would have got an answer of 19.176, which is close but not the same answer. What you've introduced is a rounding error. When you have an equation, there's always going to be a limiting reactant, and your reaction is going to continue using up the limiting reactant, forming product, until you get to the point where your limiting reactant is used up. And at that point, the reaction is going to stop. So whatever you don't want your limiting reactant to be, you always need to make sure the other one is in excess. There is loads and loads of maths in this. The majority of the content of this topic and a few other bits that come out elsewhere. You can get loads and loads of practice for this in my book, Maths, the chemistry bits. It has 60 equations for you to practice balancing, loads of titration calculations, loads of bond density calculations which come up later in the course, lots and lots of things for you to do. We can list the metals by how reactive they are, with the most reactive being at the top and the least reactive being at the bottom. Now you need to remember these. If you have any good mnemonics remembering these, you can pop these in the description below, in the comments below. That would really, really help other people. Things that are above carbon need electrolysis to be extracted, whereas things that are below carbon can just be extracted by reduction. However, things that are really, really unreactive, like silver, gold and copper, are generally found in the earth as their pure ores, unreacted with anything. Everything else is generally going to be reacted with oxygen in the form of metal oxides. You can also use this to predict the products from electrolysis. If the metal you are used in the electrolysis is more reactive than hydrogen, then you're going to get hydrogen as a gas. If it is less reactive, then you're going to get something else as a gas. And we can use this to predict the products for displacement reactions. If we reacted magnesium chloride with calcium, because calcium is more reactive than the magnesium, the calcium is going to take the place. So we are going to get calcium chloride plus magnesium as our products. However, if we reacted magnesium chloride with aluminium, because magnesium is more reactive, aluminium cannot take the place, it will not displace it, so no reaction is going to take place. When you have a redox reaction, oxidation is loss of electrons, reduction is gain of electrons. A good way to remember what the electrodes are called is that the positive electrode is the anode and negative is cathode. At each electrode in electrolysis, we're going to have oxidation and reduction taking place and movement of electrons. And the half equations need to reflect this, and they need to be balanced. The first thing we need to balance is the elements. In the first one, we have copper and copper, one on each side, that's fine. But here we have a 2+ charge, we need to make a neutral charge. The only thing we can add in is electrons, which have a negative charge. Because copper is 2+, we need to add in 2 electrons. We are adding in electrons, this is gain of electrons, so this is reduction. And because copper is positive, it will go to the negative electrode, which is the cathode. Second one is a bit more complicated because you can see fluorine ion will go to a diatomic fluorine molecule. First thing we need to do is to balance the fluorines to go in there. Now we need to balance atoms. We have 2 negatives and it needs to go to a neutral. So we need to lose something. The only thing we can lose are electrons, and to balance out the charges we need to lose 2 electrons. This is loss of electrons, so it is oxidation. Fluorine is negative, so it will go to the positive electrode. And the positive electrode is the anode. You need to remember all of the equations, remember the ions, and be able to work out what is going to come from a reaction. So if we have an acid and a metal, we are going to get a salt plus hydrogen. Acid metal oxide is going to give us a salt plus water. Acid metal hydroxide is going to be a salt plus water. Acid metal base, salt plus water. Acid plus metal carbonate is going to give us a salt, water, and carbon dioxide. To work out the formula of the salts, you need to know the formula of all of your ions. I've made flashcards to help you with this. You can watch the video. I'm afraid you're going to need to watch it over and over again so that you learn it. And then you're going to need to make sure that you combine the ions in such a way that they are neutral overall. For making a pure salt, we are going to be making copper sulfate. This is mixing sulfuric acid and copper oxide to make copper sulfate and water. You're going to need to heat the sulfuric acid, stir in the copper oxide, which is a black powder, until it is in excess, which basically means you can't dissolve it anymore. Let it cool a bit, and then you can filter the solution to remove the excess copper oxide, so that the black copper oxide powder will stay in the filter paper, and then the solution of copper sulfate will come out down the bottom. Once you have your solution of copper sulfate, you can evaporate away the water to leave you with the copper sulfate crystals. Now the size of the crystals will depend on how quickly you do this. You're going to be left with blue crystals. The blue crystals here are the hydrated ones, and the white crystals around the edge are the anhydrous ones. On the pH scale, things that have a pH 1 are acidic, pH 7, is neutral, and 14 is an alkali. The ions responsible for acidity are hydrogen ions. The ions responsible for alkalinity are hydroxide ions. The neutralisation equation is incredibly important. It comes up a lot, and that tells us that hydrogen ions plus hydroxide ions can be neutralised to produce water. To carry out a titration, first of all you need to put 25 centimetres cubed in an alkali into a conical flask, add a phenolphthalein indicator or an indicator like methyl orange, fill a burette with an acid of a known concentration, take the initial reading on the burette and record it, and while swirling the flask, use the tap to slowly add, drop by drop, the acid into the alkali. When the first permanent colour change happens, pink to clear for phenolphthalein, stop adding the acid. Record the final volume in the burette and repeat titers until you get it within 0.05 centimetres cubed. There are two indicators you can use for titrations. Phenolphthalein, which is the one you're seeing here, which in an alkali will be bright pink, and in an acid will be clear or colourless. Or methyl orange, which in an alkali you can see it's going this yellowy colour, and in an acid it will be bright red, giving us a neutralisation point where it is an orange colour. There is a big difference between strength and concentration. Strong acids are going to fully dissociate into hydrogen ions and other ions. The strong acids are hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, and chloric acid. I would expect you to know that hydrochloric acid is HCl, nitric acid is HNO3, and sulfuric acid is H2SO4. The other ones we don't have to worry about too much. Everything else is a weak acid, which means it only partially dissociates. Here we have strong and weak acids at high and low concentrations. So for our strong acid, we can see our hydroxide ions and our hydrogen ions are fully dissociated. They're not touching each other, they are separated. Here we have them at a high concentration, which means there are lots of hydroxide and hydrogen ions compared to very few water molecules. Here we have our strong acid, again fully dissociated but at a low concentration, meaning there aren't very many hydrogen or hydroxide ions in a lot of water. For our weak acids, they are only partially dissociated, so some of the hydrogen and hydroxide ions have separated and some of them haven't, meaning that we are going to get some which are still together and some which are separated. At a high concentration, there are going to be lots of acid particles for very few particles of water, whereas at a low concentration there aren't going to be very many acid molecules per molecule of water. Here we have sodium chloride. Now ionic compounds have to be molten or dissolved to be able to conduct electricity, because it's when it's in its solid state you can see that this sodium and these chlorines are not going anywhere. They're very, very fixed. However, in a liquid or a molten or a dissolved state, when these ions are free to move around, that is when they're going to be conducting electricity, and that's when you can do electrolysis. Aluminium electrolysis is a slightly different form of electrolysis. We have one electrode up here, this is our positive anode, and another electrode down here, this is our negative cathode. The molten aluminium and the cryolite is just a compound that is added to reduce the melting point of molten aluminium oxide. It's added into this reaction vessel and we get one reaction taking place down here and another reaction taking place at the top. At the bottom, at the negative cathode, we are going to be attracting the positive aluminium ions. They are going to be picking up electrons and turning into aluminium atoms. This is 3+, so it needs to pick up 3 electrons. And then at the top, at the carbon electrode, we are going to attract the negative oxygens. They are going to be losing electrons and turning into oxygen gas. Because we have 2 on this side, 2 oxygens on that side, we need 2 on that side. Which means we now have 4 negative charges, so we need to lose 4 electrons as well. This is a carbon electrode up here, and we are starting a reaction which causes oxygen gas to be evolved. Eventually, the oxygen gas will react with the carbon electrode, and we are going to lose the electrode as carbon dioxide. So the carbon dioxide will wear away the electrode eventually, so this will need to be replaced. The molten aluminium collects at the bottom and can be taken off like that, and that is how we purify aluminium. The common setups for electrolysis that you need to know are sodium chloride, sodium sulfate, copper chloride, and copper sulfate. For sodium chloride, the products you are going to get are hydrogen gas, chlorine gas, and sodium hydroxide. For copper sodium sulfate, the products you're going to get are going to be hydrogen and oxygen gas. For copper chloride, you are going to get copper and chlorine gas, and for copper sulfate, you are going to get copper and oxygen gas. When we set up electrolysis, you need positive and negative electrode. Light bulb there just to check that electricity is flowing. You can see bubbles collecting around the positive and negative electrode. Sometimes this might be a metal collecting, as in the case of copper collecting here and here in copper sulfate and copper chloride. You can test for all of the different gases coming off, for example, hydrogen, chlorine and oxygen. The test for hydrogen gas is a squeaky pop. The test for oxygen gas is relighting, glowing splint. And the test for chlorine gas is that it bleaches, damp, litmus paper. An endothermic reaction feels like it gets colder, whereas an exothermic reaction, you can feel it gets hotter. Another way of saying gets colder would be to take heat in, and another way to say get hotter would be to give heat out. Now we can make these slightly more sophisticated by replacing the word heat with the word energy. So now a sophisticated answer is that an endothermic reaction takes energy in and an exothermic reaction gives energy out. During an endothermic reaction, energy is going to get taken in, so we have our reactants down here. Energy gets taken in, so our products are up here. So we can say that the energy of the products is higher than the energy reactants. During an exothermic reaction, energy reaction is given out, so our reactants, energy is given out, so our products are going to be down here, which means our products have lower energy than the reactants. For example, an endothermic reaction would be electrolysis. An exothermic reaction would be burning or neutralisation. You need to be able to calculate the energy change when a reaction takes place, remembering that bond energy breaking takes energy in and bond making gives energy out. So burning hydrogen in oxygen will give out water. Calculate the energy change for this reaction. The first thing we need to do is write the balanced equation. Hydrogen plus oxygen gives water. We need to put a 2 there to balance out the oxygens and a 2 there to balance out the hydrogens. Draw everything we have. So we have hydrogen and we have 2 of them, so I'm going to draw that twice, plus oxygen turns into water. And while the examiner would probably expect you to be able to work out the formulas, balance the equation and draw them by yourself, they would not expect you to recall the bond energy. The bond energies will be given to you in the exam. Next we're going to list the type of bonds that we have and the number. So we have hydrogen bonds, and we have 1, 2 of those. We have an oxygen double bond, and we just have 1 double bond in there. We have oxygen-hydrogen bonds, and we have 1, 2, 3, 4 of those. And now we need to take that and multiply it by the bond energies. So 2 bonds for hydrogen, that is 2 times 4, 3, 6. 1 times 4, 9, 8. 4 times 4, 6, 4. We can do the maths and work out how much is on each side, adding those up. 872 plus 498 gives us 1370. There's just 1856 on that side. Now we need to do the energy of the reactants minus the energy of the product, so 1370 minus 1856, giving us minus 486 kilojoules per mole. In this type of equation, if you got the symbol wrong, you'd probably only lose 1 mark. It having a negative sign in front of it tells us it is exothermic. So any reaction that is burning, you can check yourself because it should always be exothermic. We can pretty much guarantee that a big calculation is going to come up on this paper, so it is worth practicing these really well. To help you, I've written a book. The rest of this video is for separate chemistry students only, so if you have finished, well done, excellent work. It was a bit of a slog this video. You can go and move on to the next video, use your revision guide. If you've got separate chemistry, I'm afraid you've got a bit more to go. Here we have a simple cell with 2 different metals, copper and zinc, in their own solution. So here is zinc in zinc sulfate solution and copper in copper sulfate solution. They are connected by a salt bridge or an ion bridge, and because zinc is higher in the electrochemical series, it is going to push electrons this way towards copper. A flow of electrons means we are going to have a potential difference. So the zinc is going to be giving up electrons and the copper is going to be accepting electrons. That thing that we commonly refer to as a battery is actually a cell. I know it's really annoying. A cell is 1 battery. A battery is more than 1 cells. So this is a cell, and then 2 or more of them together would be a battery. In non-rechargeable batteries, the chemical reaction that produces electricity, once that is used up, the battery is dead. Whereas in a rechargeable battery, there is a reversible reaction that goes on. So once the reactants are used up, you can pass electricity through it, which will cause the reaction to go in the opposite direction, recharging the battery. In a hydrogen fuel cell, we just have hydrogen gas reacting with oxygen gas and turning into water. There is a large amount of energy released. Which can be used to power an electric car. And water is the only product which means there are no carbon emissions. There are a few problems with this, predominantly with the production of hydrogen. At the moment this uses fossil fuels because hydrogen can either be made by reacting steam with coal or natural gas, which are both fossil fuels, or hydrogen is made by electrolysis of water, but that involves electricity which is generated using fossil fuels. The other problems are it's quite hard to find. The hydrogen needs to be compressed. Which is a problem because it will be explosive. It also needs a very, very large tank to store it in. And they don't work at low temperatures. At the negative electrode, we are going to have hydrogen gas minus 2 electrons turning into hydrogen ions. At the positive electrode, we are going to have these hydrogen ions reacting with the oxygen gas and some electrons, and they are then going to turn into the water. Transition metals are in the middle. Their properties are that they are hard, shiny, and are good conductors. These are basically your traditional metals, so any property of a traditional metal you can generally associate it with a transition metal. Because of their properties, they can be used in jewellery, in wires, or in saucepans. And because they get all these different colours, they can be used for things like stained glass or for coating statues. Here the Statue of Liberty has a copper coating. Copper, transition metal compounds are generally going to be blue or a bluey green. Iron 2 is light green. Iron 3 is an orangey brown, a rust colour. And cobalt is a really lovely deep rich blue. Nanotechnology is absolutely fascinating. It is taking atoms and rearranging them into specific locations or specific sizes so that we can use it. It is much, much smaller than technology. It is very small. But it is made up of lots of different atoms. Now the potentials for this are massive because as we get small we are increasing the surface area. And when we get this small, things have very, very different properties. Things look see-through, things are flexible, things start to behave very differently to they would if they were much, much larger. The potential for this is massive: communications, drug delivery, personalised medicine, but people are wary about this because it is a new technology. To work out percentage yield, you need to take your actual yields and divide it by your theoretical yields. So if this is your actual yields, then your theoretical yield is how much you thought you were going to make. To work out your atom economy, that is your MR of atoms in the required products over your MR of reactants, or the MR of stuff you wanted over the MR of the stuff you actually got. For titration calculations, we first need to calculate the number of moles of acid used. We can use this to find the number of hydrogen ions involved in the reaction. This is going to be equal to the number of hydroxide ions at the point of neutralisation. We can use this to calculate the number of moles of alkali used and concentrate the calculation of the acid. We have 25 centimetres cubed of alkali was neutralised by 15 centimetres cubed of 0.2 moles acid. Find the concentration of the alkali. First thing I'm going to do is pull all the information out of the question. Concentration of the alkali is what we're trying to find. Volume of the alkali, 25 centimetres cubed. Concentration of the acid, 0.2 moles per decimetre cubed. Volume of the acid, 15 centimetres cubed. So the first thing we do is to calculate the number of moles of acid used. So for the number of moles of acid used, we're going to use concentration of the acid times volume of the acid. That is 0.2 times the volume of the acid, which is 15, divided by 1,000 because we need it in decimetres cubed. So 0.2 times 0.015, giving us an answer of 0.003 moles. If we look at our balanced equation, we can see that acid and alkali are in a 1-to-1 ratio in this equation. So there's going to be an equal number of hydrogen and hydroxide ions. So we know that our moles of acid are 0.003 moles, which means our moles of alkali must also be 0.003 moles. Now we know the number of moles of alkali. We can use concentration by volume again, rearranging that because we know the moles and we know the volume to find the concentration. We can use moles equals concentration times volume again and rearranging that because we know our moles and we know our volume. So moles divided by volume will give us concentration. So our moles from we've just worked out is 0.003. Our concentration is 25 centimetres cubed, divided that by 1,000 to get it in decimetres cubed. So that is going to be 0.003 divided by 0.025, giving us 0.12 moles per decimetre cubed as our concentration of alkali. When you are dealing with gases, what you need to remember is that 1 mole is always going to take up 24 decimetres cubed. Well done for making it to the end of this video. You are all absolute superstars. All the best in your exams. I'm keeping all of my fingers crossed for you.